what we ended with last time, or where we had reached, was we were talking about kinetics, and our rate of reaction is related to something like the speed of the reaction. And what are we talking about? Usually when we're talking about some sort of rate, it's some time-dependent quantity, right? It depends on something happening over time. So what are we looking at changing over time in terms of chemical reactions? Right, when we're looking at kinetics, like our rate of reaction depends on what? What is the variable that we're looking at? Remember, molarity, the concentration of any of the species, right? The concentration, so this depends on the concentration of any product slash reactant in the balanced chemical equation. And then we also have the balanced chemical equation, so that also means that the stoichiometric coefficient is also important when we're looking at the rate of the reaction, right? Because if we have one product or reactant that's being consumed, and let's say we're making two products, that means for every one reactant we lose, we gain two of the product, right? So that's going to affect, or we have to include that when we talk about our rate of reaction. And it can, our rate of reaction, this can be expressed as a function of any reactant or product. All right, so we could write our rate of reaction in terms of any arbitrary reactant or product. And the general form looks something like the rate is defined as capital K, and it's either plus minus, and if it's plus or minus, that tells us what determines if it's plus minus? If it's a product or a reactant, right? If it's plus, then it's a product. If it's minus, it's a reactant, right? Because the reactant's concentration is going down as the reaction proceeds, right? So that means that that delta is going to be a negative quantity. And then we have 1 over, and I'll use the variable m, where this is just the stoichiometric coefficient. And then it was delta, the concentration of the reactant or product, over the change in time. Okay, so that's kind of where we ended off with last time. And then we kind of started going over some problems on how you can use this and how you can relate different changes in concentration if you know the rates of the reaction. Let me see if I can do this. Is that better? Give you guys a second. I'm going to go on. And so then we did some problems, so we're going to start with that again today. So we have the following reaction. We have some organic molecules, so it's like butane. When you guys go and take organic chemistry, you'll learn all about that. And it's going to go from a linear form of the molecule to two ethane molecules. And so here you're given a data table, and like I said, for a lot of kinetics, and even once we get to acids and bases, you'll be dealing with a lot of data tables. So we're going to be looking at the concentration and time changing a lot. It's asking what is the average rate of reaction between 0 and 10 seconds. So see if you can remember using the rate of reaction, right? Remember, this says the average rate of reaction, but really that's just the rate of reaction that we've talked about, right? So think about what delta means and see if you can use the data table to then come up with, there's one, again. So our rate of reaction was defined as capital K is equal to what? Generally. So for this problem, right, we're given C4, so the ethene molecule, which is C4H8. How do we relate the concentration of that species to the rate of the reaction?
Because it's on the left side, would it be negative delta C4H8 over delta T, or delta time?
So the C4, yeah, so it's on the negative side, so that's exactly right. It's going to be on the negative sign, right? So this is going to be because it's a reactant. And then the coefficient is 1 over 1, so that's just going to be 1 divided by 1. And then we're going to have the change in the concentration of C8 or C4H8 over the change in time, right? And change in time is just T final minus T initial. But here it's asking between 0 and 10 seconds. So if we write all of that out, it's going to be negative the concentrations, which will be 0.913 molar minus 1.000 molar over 10 seconds minus 0 seconds. And so when you guys go through and calculate all of that, we see that the quantity inside the parentheses I've written here is a smaller number being subtracted, or a small number minus a larger number, so that's going to be a negative quantity inside the parentheses, and so the two negative signs are going to end up canceling out there. So it should be positive, and our rate always has to be a positive quantity, right? Our rate of reaction. And so when you guys did that, what do you get for your answer? Making 0086 87. 87, what are the units of rate of reaction? Molarity over seconds, right? So it's going to be molarity per second. Right, so that would be the average rate over this time interval. Technically, if we're looking at sig figs and stuff here, and the only reason I mentioned that is because eventually we're looking at sig figs for logarithms and whatnot. Each of these has 3, but that technically only has 1 sig fig there, so there should only be 1 sig fig, so 0.009 would be 0.009 molarity per second for correct significant figures. Okay, any questions on that? No? All right. So then for the same data table, now we're asking what is the rate of formation between ethene, right? So I keep saying ethene, but that's what this molecule is, ethene, between 20 and 30 seconds. All right, so the rate of formation, instead of looking at the rate of reaction, what is the rate of formation equal to? How would we write an expression for the rate of formation? All right, our rate of reaction, again, when we looked at it, was in the general form like this here, right? Plus minus 1 over the stoichiometric coefficient, delta concentration over change in time. The rate of formation or decomposition or depletion, whatever you want to call it, that's related to just the quantity, this delta quantity here. This delta concentration over the change in time. Change in concentration over change in time is the rate of formation or the rate of decomposition. The overall rate of the reaction includes the plus or minus sign because it always has to be a positive quantity, and it includes the stoichiometric coefficient. Why? Because that's a singular value for the entire reaction, whereas the rate of formation or decomposition is for specific reactants or products in the reaction. So here we're looking at the rate of formation for ethene C2H4. That's going to be related to, or that's defined as this quantity right here. This whole thing is defined as the rate of formation. And you could do this for the previous problem, where you look at the rate of decomposition for butane, which is the C4H8, except it would just be a negative quantity since it's decomposition. Okay, so using that, see if you can come up with an answer for how to solve for this quantity. So remember, we can write the rate of the reaction in terms of the change in concentration of any of the species or the reactant or product in the reaction. So in the first part, we had K. Again, this was our rate of reaction was equal to minus the change in the concentration of butane, which is C4H8, over the change in time. This is also equal to, what is it equal to in terms of ethene here? Which is C2H4.
1/2.
1/2, right? Because the stoichiometric coefficient is 2 times the change in concentration of ethene over the change in time. Right, and what quantity have we solved for here already?
Delta C4.
Yep, we already solved for this whole quantity from part A, which is the same thing as saying that we solved for K. So since we already have the rate of the reaction, now we can look at the specific rate of formation of the product in this reaction. So we have K is equal to 1/2 delta C2H4 over delta T. We know that this is what we want to solve for. And so to solve for that, what's the only thing we have to do here? If we're just trying to isolate this ratio or quotient right here.
Multiply by the ratio.
Yep, just multiply both sides by 2, right? So times 2 times 2. These are going to cancel out. So this gives us 2 times K, which was 0.0087. What were the units of that again? Molarity per second equals delta C2H4 over delta T.
I have a question. Would it be a slower rate this time because it's from 20 to 30 seconds, so the concentrations are lower, or?
Would it be a slower rate from this time because you're going from 20 to 30 seconds? So, oh, you're right. So we have to actually use the data from 20 to 30 seconds. Yeah, I skipped over that part. Good job for pointing that out. So from 20 to 30 seconds, so we can't use this from part A. This is actually another layered layered step. So let me erase this from part A. We need to solve for, again, so instead of plugging in for K here, I'll just make a new sheet. So we're gonna go from minus delta C8 or C4H8 delta T is equal to 1/2 delta C2, H4, delta T. So the time interval is still going to be the same here since it's only going to be 10 seconds. You're just using a change in concentration that's different. Yep, go ahead.
Would it have been the same rate of reaction just for that first 10 seconds, right?
For the first 10 seconds, it would have been the same rate of the reaction. But remember, because the rate of reaction can depend on the concentration, right? So when we looked at the slopes of the curve, remember the slope is just the tangent point at the curve right there. That's changing as the reaction moves forward till reaches the flat part. And so the rate itself does change. So you can't use the K value from part A for that. If it's a non-zero order reaction. We'll talk about order reaction in a little bit, but. So we just have to plug in the values here. And so this is going to equal minus the concentration, H8, final concentration, C4, H8, initial, over, and it's going to be 30 minus 20 seconds, because we're looking at that specific time interval, is equal to 1/2 delta C2 H4 over delta D. So it's essentially the same step, it's just here we are looking at the rate at a different point in the reaction. And so I'm just going to multiply both sides by 2 here. So 2 cancels out. And we'll get 2, or -2 times, I'm just going to check the values here real quick, 0.763 molar minus 0.835 molar over 10 seconds is equal C2 H4 over delta T. So that should be equal to the rate of formation. It's the rate of formation, so it should be a positive quantity. So we can double check that here. We also see this as units of concentration in the top, units of time in the denominator. We see a concentration of units at the top here, time in the denominator, so those are working out, the units work out. This is a small number minus a larger number, so this is going to be negative inside the parentheses, and then we have a negative here as well. So this will be positive overall, which is what it should be for the rate of formation of our product here. So when I read this, I thought it was like the previous problem we did last time. Just make sure you read the entire question. And so when you plug this in, so when plugged it in, right? What did you guys get for your answer? 0.0144, and the units are molarity per second, right? And so units are always important, otherwise the number is meaningless. Delta C2 H4 over delta T. And it makes sense that the rate of formation should be larger than the rate of reaction at that point, because we have 2 products being made for every reactant that's used. Okay. And thank you again for Colin for pointing that out. And so again, I'm just gonna solve for again. This is gonna go on the next page. And here I'll put for 2 10 seconds. Okay, any questions Thumbs up, thumbs to the side, thumbs down. All right. So this is using a data table. The problem can also be phrased a different way where you don't necessarily have to solve for the rate of the reaction using the data table. You can just be given that value. And so the next example we'll deal with that. Then we're going to start talking about the order of the reaction. And reaction order and what that means in the experimental rate law. Okay. All right, so you're given an arbitrary reaction here. Like I said, you'll be seeing a lot of A, B's, and C's and D's until we get past acids and bases. And they're saying the initial rate is 0.1 molar per second at a given condition. That just means at a specific temperature and pressure. It's saying what is the change in concentration of the reactant B over the change in time under these same conditions, right? And so since B is either a reaction or a product, which one is it? It's a reactant, right? That would be the rate of what for that species? Depletion or decomposition, however you want to phrase it, right? So you're solving for the rate of depletion, right? So this is kind of what we had last time, except we're looking at a reactant, rate of decomposition. And here you're given the initial rate, and this is the rate of reaction. And that was, again, defined as uppercase K. So why don't you guys set up an expression, see if you can solve for the rate of decomposition here. For relating the rate of decomposition to the rate of the reaction for B here. The rate of reaction was uppercase K, and how is that related to the rate of decomposition of B? What's the first thing in the expression? Positive or negative, right? A plus or a minus sign. Which one is it going to be here? It'll be negative, right? Because it's a reactant in the reaction, right? So again, remember K is equal to plus minus 1 over M, where that's a stoichiometric coefficient, times the change in concentration over the change in time. All right, so it's negative because it's reactant. Then what's M here in this case? 2. So it'll be 1 over 2 times delta concentration of B over the change in time. So let's just solve for this algebraically. So we just have to plug in the numbers at the end. We just need to solve for this entire quantity. So we just multiply both sides by what? Times negative 2. 2 cancels out here. And then we get, I'm just flipping the sides, delta B over delta T is equal to minus 2 times K, where that's the rate of our reaction. So this is equal to minus 2 times 0.100 molar per second. So the rate of decomposition is then going to be minus 0.200 molar per second. All right, so with all these problems, we just need to find an expression relating the rate of formation or the change in concentration to the overall rate of the reaction. Once we have the rate of the reaction, we can then relate that to any of the species in the chemical reaction itself. So we could do the same thing here for C and for A as well, because once we have the rate of the reaction, which this problem gives, that's related to all the different species. Any questions on that? Here, for sig figs, technically, this isn't counted towards the sig figs, so the only thing that matters is the sig figs of the rate that's given here. All right, so we'll leave that as the rates of formation and stuff. We're going to start talking about reaction order now. So what's the general kinetics and how do we classify different reactions? And so how do we do that? Well, we have to determine the rate experimentally to do that. And so the rate determination is by monitoring the change in concentration of a reactant or a product over time, right? So this is what you guys are going to be doing in lab today, is you're going to be looking at the change in concentration of a permanganate ion over time, and you're going to be doing that by observing a specific property here. And so generally you withdraw samples at specific time intervals after you've initiated the reaction and then measure the concentration at that time. That can be kind of hard though, as you can imagine, if you still have reactants and products in the small sample you've drawn, because those can continue to react and change concentrations as you pull them. So generally one of the ways that people get around this and what you guys are doing in lab today is you make sure that the reaction has reached equilibrium before you pull the sample. And you just time the reaction once it's reached equilibrium, because then you're always starting from an initial time of 0 and a final time of wherever you finished the reaction. And so, like I said, you're kind of just withdrawing at various times, and you're looking at physical or chemical properties. So some things are easy to measure and other things are hard, and we'll talk a little bit about what some of those are. So one of the properties to measure and easy to observe, you don't even have to do it quantitatively, is the color. Because color is one of the things that change as reactions happen generally with different reactants and products. So as the color changes, usually that implies that the concentration is changing. And so you can use something called a spectrophotometer, and what that does is it measures the absorbance of a sample at specific wavelengths to quantitatively, so this would be kind of quantitative measure, of color. And so it measures the absorbance of your sample at different concentrations, and you use something, and you guys may have seen this in first semester chemistry, called Beer's law. And it says that the absorbance is equal to epsilon L times the concentration of whatever it is that's absorbing. This, you don't have to really worry about this equation. We're not going to be really using it because we don't have a spectrophotometer or spectrophotometers in the labs, or if we do, they're probably really old. This is the permittivity of light. This is the path length of light. Right, so usually you put in a little cuvette sample, it's just the size of the cuvette, and then that's the concentration. You can relate this, make a little calibration curve for how is the concentration related to the absorbance, and that'll always give you the concentration at specific time points. So if you start off with different initial concentrations of reactants and products, you can let each of those move towards equilibrium where they're not reacting anymore, and they'll reach different spots at each point. And so that'll allow you to then correlate what the concentration is after specific different initial conditions, would then allow you to solve for the rate of the reaction. And I know that's a lot of words. You guys will have a lot of practice over that, or practice with that today and then next week when we do all the calculations, because the first lab is a little calculation heavy. Okay, so the way this works again is it just you shine light through a sample and you just have a detector that measures how much is actually getting through. Okay. Other things we can measure are like volume and pressure, right? So if you have gaseous reactants or products, you can measure the pressure. How is the pressure changing? And so this is useful if we have gaseous reactants or products. So even if you have two gaseous reactants, you start off with an initial pressure, and let's say they combine to form 3 or 4 products. well, you guys learned in first semester chemistry with the ideal gas law, right? That it's just proportional to the number of moles. So if you make more moles of gas, the pressure is going to go up, the volume is going to change. And so once we, especially once we get to acids and bases, in ice tables and whatnot, you can use pressures in place of concentrations if you have gases, reactants, and products. We can use pressures or volumes in place of concentration in these conditions. And we'll worry about that more as we start to see. So things that are generally not appropriate to monitor would be something like flammability. This is a chemical property, meaning there's no time dependence. It's hard to measure something like flammability, combustibility are hard to measure. Anything that's an inherent physical property is hard to measure. And won't give you any information on kinetics. Physical properties of materials. Another thing that can be useless for us is mass, and so does anyone know why mass might be useless for a chemical reaction? It's why we balance chemical reactions. The reason the mass isn't useful is because as a chemical reaction happens, the mass stays the same, right? You can't create or destroy atoms in the process of a normal chemical reaction. So mass is always conserved. Conserved in chemical reactions. If you guys go far enough in physics, then you'll find there's some funky stuff where mass isn't always conserved, but in general, for classical physics, mass is always going to be conserved. And normal chemical reactions are considered classical physics for the most part. Because we cannot do alchemy with chemical reactions. We will talk a little bit about when you can. Does anyone know what alchemy is? No?
It's the prior learning of chemistry, basically. It was what we had understanding of physicality and stuff.
Yeah, and one of the big focuses of alchemy was trying to do something called transmutation, where you turn one element into another element, right? And so with chemical reactions, you can't do that. We will talk about nuclear reactions later in the semester, and with nuclear reactions, you can change elements from one into the other. But that has to deal with chemistry of the nucleus of atoms. So mass also not that useful to us for rate determination. And so this leads us to what's going to be the experimental rate law of our reaction. And so the rate of the reaction is going to depend on the concentration of one or more of the reactants in a chemical reaction. So the experimental rate law is generally going to be looking at the reactants in a chemical reaction. Why? Because we know if we're monitoring how something's changing, we always know how much of the reactant we're starting off with, right? We don't necessarily know how much of the product is present. We can infer that as the reaction proceeds, but generally the rate law is going to be written in terms of the reactants. And so if we have a chemical reaction that looks something just like A to the products. The experimental rate law says that the capital K, right? So this is the rate of reaction is equal to, and this is where we first start getting confusing with all the variables we're going to be using. Lowercase k, actually I think it's like lowercase k times the concentration of our reactant species raised to the exponent, and I'll just use m here. And so this lowercase k, this is our rate constant. It's a proportionality constant that relates the rate of the reaction to some power of the concentration of our reactant. And so the units are important for K, and it's one of the things that you guys will be expected to determine based off of the type of reaction that you're looking at. So the rate constant is our proportionality constant, and what the rate constant is there to do is always to make sure that you have the appropriate units for the rate of the reaction, right? Because the rate of reaction always has units of what? Molarity over seconds, right? So if you remember that this always has units of molarities over seconds, and you know what order the reaction is, which is going to be related to this exponent here, you'll always be able to determine what the units of lowercase k are. So A is our reactant concentration, and then M is an exponent that tells us the order of reaction. And so this isn't necessarily related to the stoichiometric coefficient. This is something that's determined experimentally, right? So everything we're looking at here is determined all determined experimentally. And it's saying if we have a reaction rate, remember when we plotted the concentration as time, generally the reaction rate changed as the concentration changed. That's what this is saying, is we're gonna kind of just arbitrarily assign some dependence of the reaction rate, the rate of reaction, to the concentration of the reactant here. And so again, this is something that can only be determined experimentally. It's kind of like saying we're gonna guess that it's a linear, quadratic, or not dependent on the concentration of the three cases that we'll be looking at. And so for a more general reaction, and there's one thing missing here, this is also going to be plus lowercase c. Let's say we have multiple reactants, the rate law will be of the form dependent on each of them, right? So here, our rate constant, lowercase k, is equal to our rate of reaction, which again was uppercase k, times the concentration of A to the n, B to the n, and C to the power of P. And it's important to remember that these are not related to stoichiometry. All right, so I know when we were looking at the rate of the reaction in terms of the rate of formation or decomposition of each of the products and reactants, the stoichiometric coefficient came in because it was 1 over that value for the rate of reaction. For the experimental rate law, these are things that need to be determined from experiment. And the reason I emphasize that is because as we move on, we start to talk about mechanisms. Remember, kinetics, we talk about how do things depend on time. We also talk about the mechanism. How do these reactions actually happen? What is the specific mechanism? That is going to be something that you assume and then from the balanced chemical equation and then use data to back up. So it's kind of the reverse of what we're doing here. And again, these are going to be related to what we call the reaction order. And again, the rate law is just dependent on the reactants of the chemical equation, because experimentally that's what we know we're starting off with. That's what we're actually putting into the reaction vessel. We know how much is there. And so the reaction order is the exponent of the concentration of that species in the rate laws. And again, this is the experimental rate law as determined experimentally. Right, so we have n equals 0, and n, if we have something, we'll just say a simple one, a to the power n. It would be this n is what we're looking at for each of these. N equals 0, this is called a 0th order reaction. N equals 1 is a first order reaction, and n equals 2 is going to be a second order reaction. These are really the ones that we focus on because they pop up a lot. Generally, things are not perfectly 0, second, or first order, and there are other powers that are possible, so you can have half-order reactions, other non-integer reactions. And most of the time, probably when you guys do your lab today, unless you're a perfect scientist, you'll get values that are not exactly 1, 2, or 0. Because again, we're just mixing stuff together, determining the different rates of the reaction, and then solving for the exponent, and usually there's some error associated with that. We're just basically saying, oh, we changed initial concentrations, let's see how the rate changes, and based off of that, can we determine roughly how the concentration, or the rate of reaction depends on the concentration. And so we'll talk about, what does this mean for each of the different rate constants and the dependence of the rate of the reaction. Yeah. Am I good to go on? All right, so in a 0th order reaction, it's independent of the reaction concentration. So if we write it out, we can see why. So let's just say, again, we have A to products. So we have uppercase K, which is equal to the rate of reaction. I abbreviate reaction just as RxN, is equal to lowercase k, which is our rate constant, times the concentration of A. Because it's 0th order, it's raised to the power of 0. This is because it's 0th order. And anything raised to the power of 0 is equal to what? 1, right? So this is equal to just lowercase k. I'm going to put lowercase there just to emphasize. This means that as the concentrations of A change, the rate of the reaction doesn't change at all. It means that it's independent of the concentration of A. And so based off of this, what do you guys think the units of K have to be for a 0th order reaction? Lowercase k, the rate constant. What are the units of uppercase K? Molarity per second, right? And in this case, for a 0th order reaction, uppercase K is equal to lowercase k, right? So lowercase k has to have units of molarity per seconds, right? What's on the left-hand side of the equation has to have the same units as what's on the right-hand side of the equation. As you guys go farther in physical sciences, you see that making sure the units work out will always tell you if you're kind of on the right track to solving the right answer. So that means that since uppercase k is equal to lowercase k, this is our rate constant. This is our rate of reaction. The units must match. And sometimes the way you'll see this, and I know this is going to be confusing, is that you write big brackets around them. Just trying to make sure that it's lower and smaller, and that means the dimensions, units, those are different ways of saying the same thing. This is saying the units of uppercase K has to equal the units of lowercase k. So the units are going to be molarity per second. And again, this means that it's going to be independent of time. The rate of reaction is not changing. And so you don't have to go through this algebra every time you do this. I think it's a little easier to remember how to solve for the units than it is to remember them, but you can just remember that a 0th order reaction has units of molarity per second as well. And I'll have a table at the end of, once we go through all of the rate laws, experimental rate laws, integrated rate laws, how there's a table that has all the information of all of it compiled into one place. Okay, we're at 9:30. All right, so let me see. We have how many more? Let's take a 10-minute break. So we'll come back. We'll finish up 0th order reactions. We also have 1st order reactions. And so in a 1st order reaction, the rate of reaction is proportional to the concentration of the reactant, and specifically it's going to be linearly proportional. So another way of saying this is technically linearly proportional, linearly dependent. All that means is it depends on it like a line does. And so we have our reaction rate of reaction, which was represented by what variable? What's the rate of reaction? K, upper or lowercase? Uppercase, right? So uppercase K is equal to, again, we have a rate constant, lowercase k, times the concentration of our species. So let's just say for a reaction that's same as before, that A goes to products to the power of 1. Right? In power of 1, we don't usually write ones in math, physics, or chemistry, so we usually leave it out. This is going to be the experimental rate law for a simple 1st order reaction. So what does that mean? That means as the concentration of A is increased, what happens to the rate of the reaction? It increases as well, right? As A goes up, this is going to go up, right? This number gets larger, that number is going to get larger. As A goes down, then this number gets smaller, right? So that means that as the reaction continues, A is going down, right? Because this is going to be a reactant in this case. The concentration of A is going down. which means that the rate is getting slower and slower as the reaction proceeds. And that's kind of what gives you that shape for first order reactions as they kind of start to, tail off to the end where they reach their value like that. Remember, the reaction rate K can be represented by the line at each point like that. And the slope of that line, right, is the rate of the reaction if it's concentration versus time. So this would be, and we'll talk more about the plots in a second, but so this is time and this is the concentration of A. That slope is getting smaller as the reaction proceeds. Right, so the rate gets smaller as the reaction proceeds. If we increase the concentration of A, then we increase the rate of reaction as well. Why? Because they're linearly proportional to each other. You do one thing to the other, you do the same thing. You do one thing to either of the variables, you do the same thing to the other. And what about the units of lowercase k? So this is the rate constant in this case. So we want the units of uppercase k to equal the units of lowercase k times the concentration of A. Uppercase K is units of what again? Molarity over second, right? So that means we need everything on the right-hand side to equal units of molarity per second, right? So what are the units of A here? The concentration of A. Molarity, right? So that means we already have units of molarity accounted for here. So for this to be molarity per seconds to match the rate constant, or the rate of the reaction, the rate constant has to have units of what? 1 over seconds, right? So that means that we need units of 1 over seconds times units of molarity. This is the units of the concentration of A. Then this has to be the units of lowercase k, our rate constant. Right, that has to be the units of our rate constant. You can also set up a little algebraic equation to solve for that as well. If you just write the units for everything, molarity per second on the left-hand side. So once you guys are done writing that, I'll do a quick little example of how you do that. Just solve for the dimensions of any of the variables in your equation there. All right, am I good to go on? All right, so let's solving for units. If we need the units on left to equal the units on the right. For any dimensional analysis problem or a problem where we're looking at the units of something, we always need the units to equal on both sides. So for example, for a first order reaction, we know the left units are molarity per second. These were the units of reaction rate. We want to solve for the units of lowercase k because we don't know that, times molarity. These are the units of the concentration of A. right? So all I did is I just wrote out the units for everything that we know in this equation right here, right? This is the units of A, we know the units of capital K, and we just want to solve for the units of lowercase a. So we just set up an algebraic equation the same way we do for anything else, except we just replace concentration of A with its units and the rate of reaction with its units as well. And so if we solve for, right, again, these, I know it's confusing, but the brackets here mean units of, so this is the units of the rate constant, right? So the units of the rate constant. So if we solve for K like that, what do we have to do to both sides? Yeah, we just need to, we want to isolate K, right? So we're just going to divide both sides by the unit molarity. So we have molarity, I'll rewrite it, units of lowercase k times molarity. We're going to divide both sides by molarity. On the right hand side, those are going to cancel out. And what about on the left hand side? They cancel out, top and bottom there. So this gives us that 1 over S equals the units of K. So I know we did on the previous page, we could, you don't have to do this whole thing to set up for the units, but if there's a lot of units, it can be a little easier to solve for them this way. We get the same thing as from the last page just by coming to the realization that, okay, well, if this is molarity per second, I already have molarity here. What's left over is 1 over seconds. Here you have a more kind of systematic way to approach solving for the units. And sometimes if I give you K or I give you the rate law and you'd have to determine the units of K, that'll be your hint for the problem for what order reaction is this, right? Because the units of K tell us also the order of the reaction for the experimental rate law. Okay, so that was just an aside, just working with dimensional analysis. I think there's one skill you can take away from chemistry. Dimensional analysis is probably one of the more important ones. You can figure out a lot of stuff just by looking at things that way. Okay, so that's for first order reactions. That's what our experimental rate law is going to be. Are there any questions on first order reactions? No? All right. Okay, so then we have second order reactions. So in a second order reaction, our exponent is going to be 2. So our rate of reaction is going to be proportional to the square of the concentration of the reactant. So let's say we had, again, something simple like A goes to products. Then our reaction rate is equal to uppercase K, which is equal to lowercase k, our rate of reaction, times the concentration of our reactant to the power of 2. And again, this power of 2 is what makes it second order. So now we have, we would say, mathematically a quadratic dependence on A, or parabolic, because as we increase the concentration of A, the rate of reaction doesn't just get doubled. If we double A, it'll get quadrupled because it's twice, 2 to the power of 2 dependent on A. And so we'll go through an example of how you can determine that just by looking at the reaction rate, the order of the reaction in that regard. And so if A doubles, then K quadruples. And so let me just, and so we can see that if we write K is equal to lowercase k times A squared. If we double the concentration of A, that means we're just going to replace the concentration of A with 2 times the concentration of A. And we want to see how does that affect the overall reaction rate. So I'm going to put double A. I'm just going to put a subscript there. So it's going to be the same proportionality constant times 2 times the concentration of A squared. Right? Whenever we have parentheses raised to an exponent, if they're multiplied to each other, that's just each of these raised to the power of 2. All right, so I'm going to break down the math here. So that's going to be lowercase k times 2 squared times the concentration of A squared. All right, because if we have A and B squared, that's equal to A squared times B squared. That's just our mathematical identity there. And 2 to the power of 2 is what? 4. So this is going to be 4 lowercase k concentration of A squared, like that. And if we look at what we originally wrote, lowercase k times the concentration of A squared is just equal to our original rate constant, or rate of reaction, not rate constant, our original rate of reaction. All right, so this right here is k, I'm going to put in parentheses, original. Sorry, I know my handwriting's a little bad there. K original. So if we just put all that together, we just connect this all the way to that. That'll give us K, write that more capital looking, K double A is equal to 4 times K original. Right, so we can see if we just plug in a 2 there, then that's going to quadruple, but this is why it's quadruple, right? We're just replacing, and this will be important when we look at half-lives too. Well, where do we get the equation for a half-life? Because that's related to kinetics. Well, we're just plugging in some concentration value by 2 times or 1/2 or whatever. So whatever we do to the concentration, we can always see how that affects the rate of the reaction just by replacing whatever is under the exponent here with whatever you're changing the concentration by. So you could also do it to the power. What if we 3 times the concentration? What does that do? Well, you just do the same procedure here. You have 3 times A squared, and then you go through these exact steps, and that'll tell you whatever number's left over when you've rewritten or substituted the original rate constant, not rate constant, rate of reaction back in there. That number tells you how you're affecting the new rate of reaction. So this gives you an explicit relationship between the new rate of reaction after you change the concentration and the original rate of the reaction. So simply we just doubled the concentration, quadrupled the rate of the reaction. What do you guys think it would be if we tripled the rate of the concentration? I don't think you can say it simply. 9 times, yeah, whatever the adjective is for multiplying it by 9, right? It'd be 9 times. And we'll go through an example of that here. So depending on the order of the reaction, you can always kind of figure out how the effect of the concentration affects the rate of the reaction, right? So again, the rate was uppercase K, and it was in units of molarity per second. That's not that important for this table, but I'm just emphasizing it a lot, hint, hint. And so for zeroth order reaction, right, zeroth order reaction, again, was uppercase K is equal to lowercase k times a to the power 0, right? So if we double the concentration, how does that affect the rate of the reaction? Right? So the same way we did it for the previous page, we can do it here. We have 2 times concentration of A. So we have uppercase equals lowercase times 2 times the concentration of A to the power of 0. We just put it all under that exponent, right? So we put it all under that exponent. And what's 2 times A to the power of 0? 1. Anything to the power of 0 is 1, right? So this is always going to be equal to lowercase k. And this should make sense to us because, well, we knew that for a zeroth order reaction, the rate of the reaction does not depend on the concentration. So changing the concentration shouldn't affect it at all, right? So that's how we say it mathematically, and then intuitively know that it's not dependent on it, so it shouldn't change it at all. So the rate is just going to be lowercase k again. The effect of doubling the concentration is no effect. Let me see, what am I writing? Because no effect, because when we plug it in, we still get k there. So why don't you guys take a second, see if you can figure it out for first. So first was the power 1. I'll just write the concentrations here. Second, we did already, but you guys can do it again if you want to reinforce it. Negative is going to be -1, and then half. Like I said, we don't really see that at all, but it's just good practice. Half is to the power 1/2. Power 1/2 is the same thing as doing what? Does anyone remember?
You can go slower, but I don't know.
It will be, it's a very slight increase, but the same thing as taking the square root, right? Power 1/2. 1/2 is the same thing as the square root of k. Again, that isn't super important for completing this. You're just going to use the same strategy you did before. Should be 2, so it should be 2 times the original. Right. Second, we know was 4, so it's 4 times the original, and the only weird ones are the ones that aren't really going to show up a lot, except maybe it's like a test question for solving the rate constant or seeing how well you understand the dependence of the rate of reaction on the concentration. Does anyone have an answer for negative?
-2.
So it should still be a positive number, right? Because the rate of the reaction is always going to be what? Positive. So the only thing we're doing here is replacing it with a -1. So if we have k is equal to lowercase k, and then we have A, the effect of doubling the concentration, sorry. So it's going to be 2 times A, all to the power of -1, right? Power of -1 is, what's another way of writing that? 1 over that power, right? So this is equal to the rate constant times 1 over 2 times A. Oops, fix that parentheses. So then this will be the rate constant. We'll pull out a 1/2. time 1/2 rate constant times 1 over A. This right here, let me put the laser pointer, this right here is our original rate of reaction. And what we have left over is a 1/2. Right, so what this does is it effectively 1/2 the original rate. So it's 1/2 K original. I didn't write it there, but you can, this part right here is the same thing as the original rate. Does everyone see that? Because the original rate is equal to K times 1 over the concentration of A. So once I saw that this was right there, I just see whatever's left over, and that's how that rate of reaction is affected. Right, so this is lowercase k. Let me write that better. Lowercase k, that's our lowercase here. This k times 1 over a, k times 1 over a, that's our original. We just had an extra 2 here because we doubled the concentration, right? We just put whatever was under the exponent here. And then just kind of working through the algebra, eventually you get that. When you double the concentration for a negative order reaction, you 1/2 the original reaction rate. This is kind of a weird dependence, but not completely out of the realm of possibility. To be like if you added an inhibitor to like a biological reaction or something. All right, and then does anyone have any idea for the half reaction? This one's a little funkier just because a little bit more just how much you remember from math, but this is just going to have a 2 to the 1/2. Let me keep the color the same. 2 to the 1/2 is left over, so it's going to be 2 to the 1/2, which I think like 1.44 times K original. So it just multiplies it by a small factor, not exactly 2, not 1, but somewhere in between both. And if you go through and do the exact same thing there, you just replace the -1 with a 1/2, you can do the same thing, just by using the rules of exponents and stuff. All right, so these are just what happens if we double the concentration. You could do the exact same thing if you triple it, quadruple it. The only thing that changes is instead of a 2 raised to the power of whatever, it's going to be whatever you're changing the concentration by. All right, any questions on that? No? All right. And so if we're looking at different types of plots, so we've looked at these before, on the left-hand side. We've looked at how the concentration can change versus time. So now we have explicit forms for each of the different reaction orders that we're going to be focusing on. For a 0th order reaction, the concentration or the rate of the reaction doesn't change as the concentration changes, right? So it just means whatever the reaction constant is, that's going to be the same rate the entire time. So it's just a line, right? It's just going to linearly increase all the way down to 0 there if it's a reactant. For 1st order, it does change, so that's why we have that slope, right? As the concentration of A gets lower, the rate of the reaction gets lower. And then same thing for 2nd order, except it's even stronger dependence, right? We see that the reaction is getting slower faster because we're depleting. It's more dependent on the concentration of A. You can also look at how the rate is affected or dependent on the concentration. So this is similar to our, experimental rate laws, right? Because our experimental rate law relates capital K to the concentration of A in each of these cases. And then this is going to be related to just the concentration versus time. And on Monday, we'll talk about the integrated rate laws because that's what that's related to. And you see that for a 0th order reaction, there's no dependence, so it's just a flat line, right? the rate of reaction doesn't change as we change the concentration, so that's why it's just a flat line up there. For first order, it's a linear dependence. If we increase the concentration, so as this number gets larger, then this number gets larger, so that's why we just have a straight line. And then for second order, again, remember it's also quadratic or parabolic, which is why it looks like half a parabola there. As you increase the concentration, it gets the rate gets faster and faster. It gets faster unit to the power 2 as A increases. So those are 2 types of plots that you can look at. So for example, another way you can word a problem is I don't necessarily tell you the order of the reaction. I say, okay, here's a plot of the concentration versus time, or the rate versus the rate of the reaction versus the concentration, and then that tells you what type of reaction you have as well. Right, so we're gonna be looking a lot of looking kind of at data analysis. And so now, how do we determine the experimental rate law? So first, the order of the reaction with respect to each reactant and catalyst must be found. We're not going to be worried about the catalyst here, so you don't have to worry about that much. But you want to find the order with respect to each reactant. So we've been looking at, for simple reactions where it's just A goes to product. Remember, the more general form, we can have multiple reactants, and it's, each reactant has an independent order. So if we had, for example, A plus B goes to C, the experimental rate law will be K times lowercase k, A to the power M, B to the power N, right? And one thing we hadn't discussed in detail is that, well, in the rate law, each N or N here can be determined independently, and the reaction can be dependent differently on each of those reactants, meaning that it can be first order in A and 0th order in B in this case. And so, like I said, with the first lab, there's going to be a lot of kind of practice doing this. How do we find M and N? And generally, the way that that's done is you can vary the concentration of one and leave the other one the same. That way, you're saying, okay, this is just how the reaction rate depends on A if we don't change B at all. All right, so this just means solving for M and N, for example. And this is why we kind of focus on doing first, second, and 0th order, is because those are easier to observe by eye. If we double the concentration and the rate doubles, that tells us it's first order. If the rate quadruples, that tells us it's second order. If it doesn't change, then that's going to be 0th order. And so the way that you guys are going to be doing this in lab is you're going to be looking at a series of experiments done in which the concentration of reactants are varied. And usually they're going to be doubled, right? So that's why we did the whole table of, well, how does the doubling of the reactants affect the rate constant? Because it's easy to see by eye. You can go through and you can determine, get a bunch of other ratios and stuff too, but those are the ones that are easy to see. And in red here I have run to completion, right? Because that was kind of the trick that you do, is that you start with an initial amount, you let the reaction run until you know it's fully done, you stop the timer, that gives you the time interval. This allows you to then always start the initial time at time equals 0. This means initial is always equal to 0, right? So when we're looking at the rate of reaction, delta T is equal to T final minus T initial is just equal to T final. That's why we generally run to completion. So again, in today's lab, you're going to be starting off with a very purple solution. Going to let a reaction run. Once it turns amber and all the purple's gone, then you know the reaction's done, you stop your timer. Then you now know what is delta T. Delta the concentration too, because you'll know you've depleted all of the reactant in that case as well. So that's kind of the trick to this, so we're not taking a bunch of individual time points. Okay. And so let's go through an example of how exactly we would solve for M or N in this scenario. We'll start off first with a simple one where we only have one reactant. Oops. All right, so we have this chemical reaction, right? Nitrous oxide. And we have the initial concentrations, right? So these are what these tables are going to look like. We have a series of experiments, right? We have two, the smallest series that we can have. So we have experiment 1, we start off with a concentration of 0.01 molar. In experiment 2, we start off with a concentration of 0.02 molar, right? So what have we done to the concentration between these two? We've doubled the concentration. So we're looking at the effects, and oftentimes that's what we're going to do. We're going to double the concentration. So we double the concentration, and then we measured some rate, right? So this is, you're going to physically do this in lab by using a stopwatch, and then the change in concentration just by the amount, calculate the initial moles that you have. So we see the initial rate is 4.8 times 10 to the negative 6, and the final rate is 9.6 times 10 to the minus 6. And the units of these are going to be molarity per second. So what happened to the rate when we doubled the concentration? We doubled both of them, right? And so then that should tell us what the exponent is, because if the rate doubles when the concentration is doubled, that should be a first order reaction, right? So both of these, we doubled the concentration of N2O5, and then we see that the reaction rate, uppercase K, also doubles. Just by looking at this, we can see that this should be first order, because on our table that we did before, if we double the rate or double the concentration and the rate doubles, that means it's first order. So we can say just by observation, the reaction is first order in N2O5. Right, the reaction is going to be first order in N2O5, right? Because that's our reactant there, and that's what we're varying in these series of experiments. So if you had to write an expression for the experimental rate law, how would you write that expression for this reaction? If it's first order, that means there should be a power of what somewhere? 1, right? There should be a power of 1. We can just say we have uppercase K is equal to, and what always has to be there to make sure the units work out right? Lowercase k, our rate constant, times the concentration of N2O5 to the power of 1. So that would be our experimental rate law. In lab, you'll have to write this out by also solving for k, lowercase k as well, and we'll do that in a second. But this is just, if we're just writing an expression for the rate law, this is what we would get from our experiment, right? This is something that's determined experimentally, and we find that, the exponent has to be 1 just based off of observation of this table. We can also do this a little bit more analytically, right? And in lab, you're going to have to do that because I predict that not everyone is going to get a perfect doubling of your rate that you measure every single time you do this. So we also want to find a way to solve for this explicitly without just saying, okay, well that doubled, this doubled, that means it has to be order 1. So how would we do that? Well, if this is our rate law, this is before even determining what the order of the reaction is, and we have 2 experiments. We can take the ratio of experiment 2 to the ratio of experiment 1, right? And if we do that, that means we're going to plug in our rate for 2 over our rate for 1 is equal to the rate constant times N2O5 2 to the power of m into 05 subscript 1 to the power of m. Right, I put these subscripts here because for each of these experiments, these are different, right? So these are actually different values from each other, right? In the table it says that, we started off with 0.01 for this one and 0.02 molar for this one. That's why we have to have two different values. But if we have something where we have x to the 2 over y to the power of 2, right? How can we simplify that? Similar, it's like kind of the opposite of what we did with multiplication. We can combine them into one ratio to the power of 2, right? So it'd be x over y to the power of 2. Right, so that's how we're going to use that to simplify here, right? Because we have two m's right now, that seems a little complicated to solve. And what about the rate constant? What do we do with the rate constant? Right, lowercase k here. Is lowercase k going to be different between these two experiments? No, lowercase k is a constant value for this reaction. So that's going to be the same. So what should happen to lowercase k then?
Just cancel out.
It should cancel out, right? So lowercase k cancels out, which is good because we haven't solved for that yet. We want to be able to solve for this independently. So lowercase k cancels out. Let me see if I can erase this without... I couldn't. So those cancel out. And then we can simplify this a little bit more because now this is equal to the ratio n2 05 2 over the ratio n2 05 power of 1 to the power, subscript 1 power of n, right? So these two things are equal to each other. And so now we know that if we don't have perfect half doubling or quadrupling of these values, that we can just take these ratios and then we can actually solve for m explicitly. And so if we have K2 over K1 is equal to N2 05 subscript 1 to the power of n. Does anyone know how we can solve for k here? I mean, it's not k, solve for n. So generally, if you want to bring an exponent down, you can take the logarithm of both sides, and that brings the exponent. Let me make another page. So this brings the exponent. We're going to take the logarithm of both sides. I'll write that here first. Logarithm of both sides. And when we do that, am I good to go to the next page, or are you guys still writing? That's something that I don't like about slides. No?
Can you define the logarithm?
Yeah, I'm going to do that in the next thing, right? So the logarithm is basically an operation that is the counter operation or the inverse of exponentiating something, right? So the logarithm, you can do log base 10 or log base e are the two common ones. That's a natural logarithm and log base 10. And so when you take the logarithm of, and we'll do a couple rules here, we have x to the power of y. The logarithm of this is going to be y times the power of x. If we have the logarithm of x times b, that's equal to the logarithm of x plus the logarithm of b. And if you have the logarithm of x times a or sorry, not x times a, x over a. This is equal to the logarithm of x minus the logarithm of a. Those are just some basic logarithmic identities. And what's useful for us in this case is that when you take the logarithm of something that has a power, it brings the power out of the exponent and in front of the logarithm. And the logarithm is really just a button on the calculator that you press. And what the logarithm is asking you is, so for log base 10, it's saying 10 to the power of what is equal to this value. And you're solving for that power of what. So log base 10, what it's asking of something like 2. This is equivalent to saying 10 to the power of what is equal to 2. All right, that's what you're solving for when you plug this in the calculator. So this is just and we'll talk more about logarithms and stuff probably next time. But really, it's just the inverse operation of doing an exponent is what a logarithm is. The same way multiplication, inverse is division. Exponentiating, raising something to a power, logarithm is the inverse of that. And so when we have a whole equation, right? So now we get back to, actually let me add, is anyone have any other questions on logarithms? We don't have to get the full, philosophy of what a logarithm is and stuff, because there's people that spent hundreds of years kind of figuring that out. Euler was one of them. But just using it is all that really matters for us when we need to use it. It's when you guys did pH calculations, the logarithm is involved there, log of the hydronium concentration. So logarithm of both sides. So we're going to do log K2 over K1 is equal to the logarithm of the concentration N2O5 2 over N2O5 1, all of this to the power of m. So now we can take m outside of the logarithm, right? Because our first identity, which is the important one there. So this simplifies to the logarithm K2, K1 equals m, the logarithm N2O5 subscript 2, N2O5 subscript 1. And now, right, so we took the m, which all of this was raised to, and we just brought it outside. So now we can actually just solve for m, because this is just a number we plug into our calculator, and this is just a number we plug into our calculator. So we divide this side and that side by the logarithm of this whole thing right here, and then that gives us an expression for n. And right now it looks complicated because I've left everything in terms of the variables, K2, K1, these concentrations, right? But if we think back to what they were, the ratio of N2O5 to N2, initially in experiment 1 and experiment 2, this was, what did we do to the concentration? Does anyone remember? I know it was a bit ago then. We doubled it, right? So that means that this is just equal to 2, right? And what happened to the rate when we doubled the concentration? It doubled as well, right? Because I know it was a while ago when we talked about it, right? The rate doubled and the concentration. We doubled the concentration, doubled the rate, right? So actually what's going to happen is this is going to be the logarithm of 2. If you plug in the numbers, this will be 2. And this is also the logarithm of 2. So if we take this number and divide it by the same number, we should get what? If we take two numbers, identical numbers, and divide them by each other,
Just 1.
it's 1, right? which makes sense, right? Because we said that this should be first order just by looking at the plot. But when you plug all this in, you'll also get that m is equal to 1. So it was a lot easier to do it the other way just by observation. But this is useful for when we don't have exact numbers, right? Because we can just plug these numbers into a calculator. And at this point, you could plug numbers in right now. Let's say it wasn't doubled or something. You just plug in whatever this number is, take the logarithm of that in your calculator, plug in these numbers, take the logarithm of that in your calculator, and then divide this number by that number, and that'll give you n. So this is how we do it explicitly. So I'm just wanting to make sure you guys had a chance to finish writing all of that. And so when we go to the next page, it'll be the logarithm. I'm going to rewrite it real quick actually, just so that I can go through all the steps explicitly, because the first time that we're seeing this. Copy. How do I? Okay. Didn't I just copy, paste there? And so we're going to divide both sides by the logarithm into 05, and I know I'm going over time a little bit here, but this is the last thing. Into 05, 1, 2, 205, 1. These are going to cancel out on this side. So the logarithm k2, k1 over, and really it's just the logarithm of this ratio of concentrations that's really annoying to write. N2, 05, 1 is equal to m. And then we know from the table these ratios equal to, which means that m is going to equal 1, just like with what we thought it would have been. But they don't have to equal to. You can plug in the numbers and you'll see that they equal to.